welcome back to my YouTube channel. In the following video, I will resume our SPM Physics Chapter 3. It's a Form 5 Physics. I hope you have gone through my first video prior in watching this one, because there are some, it's actually connected. It's related. This video content from this video is related to my previous video. Now at this point of time, we would expect my viewer should have been gone through the your reference text. Assume that you are a Malaysian student and you would have the reference textbook with you already. One thing I would like to highlight would be the application of electromagnetics that I have highlighted in my previous video. I emphasize and I insist that you should read on the applications of electromagnet as stated in the book, because it will definitely comes out in your exam. You get to know the 3 to 5 the application of the electromagnetics. I think the rest will become quite easier for you to comprehend. Now, in this video, Chapter 3, Part 2, it will be on the direction of force. It's actually mainly on the force. Okay? On the force on the conductor. Okay? Force on the conductor. So, it's actually 3 of them: the force, the magnetic field, and current. Meaning the movement of electron. Okay, so this video is all about the relationship between the force, the magnetic field, capital M, and current. Okay, in my previous video, it's all about the right hand grips rule, where you have normally a solenoid and you use right hand grips rule to find out where's the direction. Over here, lower left hand corner, you have a solenoid. All you need to do is you walk this circuit, and where's the positive? This is positive, this is negative. So what happened? Positive one around here. So what happened? Go downwards. So forefinger point down, the thumb point towards there. So here would be north, and the other end would be south pole. Okay. So right hand grip rule will be used to identify the direction for solenoid, as well as with you have straight wire, and you use right hand grip rule to find out the direction of the magnetic field. Okay, those arrow represents if you were to have a compass, that it will point upwards if you put near here, and if you have a compass put the top here, then it will point to the left, and if you have another compass put here, it will point downwards, and if you have another compass here, it will point to the right. Okay, I hope you have gone through those reading, and you have gone through the exercise, objective question. So for this video, we are going to find out their relationship, and quite often I would name this as the happy family law. It's not in the book, but this is for you to memorize. Is happy family. What is happy family? In a family, they're going to have father, mother, children. Father, mother, children is a standard. Family, you have that, and it's represented by using your left hand, and it's called the left hand. Yes, I hope you got it already. Fleming. Left hand Fleming's rule. Okay, So what's left hand Fleming rules? Left hand Fleming's rule is about father, mother, children. So what's father? Father represented by the thumb. This is force. Index finger, magnetic field. Middle finger is your current. Okay. So this is an analogy, a cartoon analogy. I never ask you to to write this on your finger. No, it's not the case. It's just that maybe you want to put your finger out. Okay. Father is a thumb, mother, and children. Okay. So how do you represent it? Okay, it's represented by this way. Now, this is the direction of force where the point. So, if you were to have a magnetic field point towards the north pole, that's the north pole. This is where the north to south. North to south. So, meaning you were to have a north to south. So this finger point towards that. Okay. Then if you were to have a current comes out. Okay. Pointing out meaning is a dot. Okay. A dot represents by a current come out. Then you would expect a force pushing this wire carrying current, pushing it upwards. And all of this direction, it's always perpendicular. Okay. Never mind. You just go to this left hand, Fleming's rule. Father, mother, children, force, magnetic field, current. So current will be always from the positive to negative. You go from positive to negative, and that's the direction. Go upwards. They are always 90 degree. Okay. Look at your finger. For your finger, they are always 90 degree, and the one here, they are always perpendicular. That's the word. Perpendicular means each of the quantity, the physical quantity, they are always 90 degree. Okay, they got to make sure they are always tangential. 90 degree to each other, perpendicular. So, how would make use of this? Okay, how we make use? It will be if you were to have magnetic field. If you were to provide, let's say, if you were to provide. If in the system of current, you will see you provide magnetic field and you provide current, magnetic field, current, what you get? You are going to get a force, and this force is called the magnetic force because this force is caused by magnetic field, or F small b, magnetic force. Or we don't do a B first. Let's talk. Don't want to confuse you at this point. Maybe you talk about M. Okay, magnetic force. Or actually, it's a B, so magnetic field, because force is magnetic field. The next video, it will be what happened when I were to provide magnetic field or magnetic. If they were in the magnetic field and you give a push or a movement, or you provide a force, this is what you get, current, or another term is called induced current. Okay, so this part is on the next part, and this is the essence for this part where you provide magnetic field and current, you get magnetic force. Now, I would have a video actually to, a practical video to show you how does it work. Meaning, I provide current, I provide magnetic field, and then they will have a force. Okay, like this one here. Provide magnetic field, I provide current, direct current. You will get a force. Okay, that's my YouTube video. You may click on the link here. I embedded here. You may click on the link, and then you're able to see this movement, this coil movement in slow motion, so that it will convince you that you will get a force. Now, over this video, there are a few things you can get from here. Is that you have no idea. You are given a magnet. Those are actually a conductor, non-magnetic conductor, meaning it conducts electricity, but it will not be attracted to the magnet. The same goes with the copper coil. Now, this coil, there are actually 10 winding. The winding direction is in clockwise direction. I wind it. I know it because I wind it. Okay, I go around. I make around 10 rounds, and then come back here, and then this entire knot go up from there, and then something good about this conductor. This coil is it's being insulated. Okay, it's insulated. It's a dark brown, but it doesn't conduct. So what can I do is I sand off the insulator. So that's why you see a different color here. This is a peach yellow, and then here's dark brown. So because I want to conduct, I want to pass through electron, I want to pass through current through it. So what happened? The current flows around this coil, and in the event if I doesn't know which is north pole, which part, because this is actually aluminium, it is not attracted to the magnet, so I got to put 2 magnets, so we will make this magnet stick onto this metal. So after the experiment, I get to know that, oh, okay, the force is from north, pointing outwards. Okay, and how do I know is that because when I conduct, I put in the current. Okay, either side current, then the direction, I look at the direction, and it turns out that the direction is actually downwards. Okay, meaning the coil will actually rotate over a counter-clockwise direction. That's why I know this is where the magnet, this is the north pole for this magnet. So the magnet going outwards, father, mother, children, force, magnetic field, current. So if my magnetic field is pointing to the right, so my index finger to the right, you should practice this while you're watching it, to the right, and then current flow from positive to negative. This side will be positive, this side will be negative later. So in clockwise direction. So what happened over here? The current would flow up. This is where the current flow. Current. Okay. So you have magnetic field from left to right, current up. Down to up. So your thumb are supposed to point downwards now. You got it? You may pause this video to apply the Fleming left-hand rule. So you will expect a force is going to pull this coil downwards, and because of the rotation, what happened? The momentum will push it downwards. So therefore this side will have a upward force. You push outwards because it's downwards force, coupling force. This couple force is a couple, isn't it? A twin, a pair, so a couple. One down, one up. Therefore, you get a rotation. Got it? This side I didn't put a magnet. It should have both sides so that you can enhance the rotation. But I don't want to do that so that I can actually tell which side is my magnet. and I can actually give a push. You will look at it to verify this law. Alright? So this is how you apply the left-hand Fleming's rule on actually a motor rules, or maybe some book you will write this as a motor rules in some reference text. Okay, motor rules is actually the Fleming left-hand rule. Or in some other experiment, they will have this catapult effect. Maybe you want to read on it. I mean, read on what does it mean by catapult effect. I mean, for your own practice exercise. Okay, so they always the case where you provide, as long as you provide the condition, the provide magnetic field, you provide current, you get a force, and you need to identify where's the direction of the force. It's down or up. How you do that? You make use of Fleming left-hand rule. Okay. Now that's all about this this part of the video. Before we proceed to the next video and continuation from our first video, how about in some cases it is not in a coil, but instead it is in a current, I mean it's in a straight wire. This is also the essence where in some modeling or in some design, what happened, you have a straight wire, they are placed close to each other, and your observer, your eye is on top here. You get a top view, and the current, one flows up while another flow down. Okay, so in my previous video I'll show you how to determine the magnetic field. Okay, the strength of the magnetic field determined by the pattern. The closer the pattern, the stronger would be the field. Okay, I mean you have gone through that already, I'm sure you know that by now. But what happened now, it would be, the pattern would be like, okay, you here go up, meaning you have a dot left, here downwards, arrow downwards, so you get a cross because it's into the plane. Your eye is here. What happened? You have magnetic field. Okay, how do you determine the direction of magnetic field? It's by right hand grips rule, right? So if you were to have a compass, you put it near here, what happened? You get downwards, right? So all the way downwards, so down and up, 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 right? Then this one is going downwards, so right hand grips rule, so you get grips around it here, right hand poke into this surface, then what happened? It grips around here, right? So down, up, down, down, up, up, right? So what happened in the middle region? So this is what I've learned in the previous video, from a previous video. So what happened now is, how to determine where is the force? If you are in the middle of this region, what happened? Okay, what happened? Here you have magnetic field. This one is magnetic field. You have current. Then in this region here, you are going to have some force, right? Called magnetic force. So where would the direction of force? Okay. Again, you make use of left-hand Fleming's rule. Now, here, what you can get here is the magnetic field. Magnetic field over this region, it's always pointing upwards. So, upwards, right? So this is the magnetic field. I would label it as B, is magnetic field. Okay, magnetic field is B, or actually unit. Okay, it's not unit. Unit is Tesla. Magnetic field unit is Tesla. B, it would be a symbol. So I don't want to. Yeah. Okay. Since we didn't do mutual induction, so I'll make do M is magnetic field. M upwards. Current for this left side, it's pointing upwards, right? So it's towards your eye. Then the magnetic field upwards. So therefore, the net force or the magnetic force from this side, left side, would be to the left. M. Okay? Magnetic force. Likewise, over this side of the wire, father, mother, children. So current into it. So therefore, the force is to the right. So therefore, what happened when you apply current? What happened? If it were to be a strip of wire or a very thin strip of wire, therefore the magnetic field will pull it apart. Okay, if you look from side, end result would be something look like, okay, you have two sides, two tops. Top side, the holder, current flow from positive to negative, then positive to negative, downwards, right? So what happened? The end result would look like this, the wire. Because the magnetic force is pushing it upwards. Pushing it upwards. This is the force. Okay? So basically this is what you need to know. And the same is true what happens if when there are two wire come together, what happen would it be? Okay, the same rules apply. You may want to practice it. It's just that when you have two wire, maybe I'll just sketch you the schematic for practice purpose. And then your wire, okay, initially without current, and then your eye is from top view. Okay, then what happened when current go up for both sides? Okay, then that would be, you have one dot because it's going towards you, it's a dot, going towards you is a dot. The end result I hope you something we don't have, that yet. I mean, so what happened? The end result, it's actually the outer part would be okay. I mean, yeah, those in front nearer to it, nearer to the source, I think they will still have magnetic field, but when they collide, what happened? It cancels off the effect. Okay. So the region in the middle is actually a neutral point. Meaning it cancels off the effect. Okay? Because the current, I hope you get it. I mean, you may pause this video and really analyze what happened between here. And you should get a force to the left, I mean from left to right, and then another force from right to left. Equal magnitude, and therefore it cancels off each other. Okay? So the moral value of story, when you have a current flow in the same direction, what happened? It cancels off. When they are in opposite direction, like here, opposite direction, when they are in opposite direction, they repel. Okay? It's a repulsive force. So basically this is all about it. I would really recommend you to go through your textbook or reference, because you really need to know about this motor rule, and then to really get used to your left-hand Fleming's rule. In your reference text, I mean the setup of your motor rules is different than from here. That I will talk about it in the next video. Now, if this is the first time watching my video, kindly subscribe to my channel. I really like those thumbs up button, either you like here in YouTube or my Facebook fan page, because it's not only help you, I think it helps the others. Stay tuned to my next video. Thank you.